Okay, so we're gonna continue with partial fractions. So let's pick up where we left off. Where's my notes? There they are. Yes, nice, cool. So let's scroll up to the top. So we learned. So one of the big things that I always like to remind you is that what we're doing is we're trying to find antiderivatives, right? And the easiest way to find antiderivatives is just to rewrite a derivative law. Okay, but sometimes you don't have that, right? And what's the whole reason you want antiderivatives? Well, to use the fundamental theorem of calculus. And you don't really want to have to use a numerical method like the limit over Riemann sum to calculate a definite integral. So you really want to find that antiderivative. So like as I was saying, we have like these tricks to find antiderivatives, things like U substitution, integration by parts, trig integrals, trig substitution, and then finally we get to partial fractions. And the whole idea behind partial fractions is that you know that the antiderivative of 1 over x is natural log x, and you take advantage of this. So like I have this example here where you can do a u substitution to solve that, because your 2x is the derivative of the bottom, which is x squared plus 1, right? You can rewrite that. You can set your u equal to x squared plus 1. You calculate your du, it's going to be 2x dx, and then you're like, oh, holy shit, that's the integral of 1 over u du, which is going to give me natural log u, and you get your answer. Bang, bang, bang. Or that was not the proper thing, the idiom. I can't remember what it is, but I just made that up there. I feel like Rick, you know, who's here watches Rick and Morty? Okay, you know how like he just sometimes gives out like random catchphrases and it like vaguely sounds like something real? I was like, yeah, we're just gonna go with it. We're just rolling with it. He actually did that one time where he was like, he like said something ridiculous. He's like, yeah, I'm owning that. And he says it like 3 more times in a row. Wubba dubba love dub or whatever it is means like, I'm in pain and help me. But there's this one particular thing that he said where he's like, I'm just owning it. Does anyone happen to remember the episode? Like, he just straight up says, like, yeah, no, I feel this. I'm just gonna say it. It was like something sort of ridiculous, like Ricky Tikki Tacky or something like that. I think Brian is Googling it for us. The research department is hard at work. We'll give the research department a moment to find it. Yeah. There's a whole page of it. So what is it? He says something like, yeah, I'm owning it. That's my catchphrase now. Yeah, yes! Yes, Stone Cold Steve Austin. But he didn't say quite that. He said something else. But I'm owning it. I'm owning my thing today. Wing, bing, bang. There we go. Go for it. Let's see. Beth, I'm going back in there. I'm getting Tommy and I'm fixing this, Rick. Whatever you say, Stone Cold Steve Austin. I don't know why I just said that. It doesn't make a lot of sense, but I'm gonna stand by it. Whatever you say, Stone Cold Steve Austin. I'm owning it. Yeah, that's exactly what I was thinking of. Yes. He just said like this random thing. I was like, fuck it. Yeah, that's what we're saying today. So, back to math. Boom. We had this example here where the top was not just the derivative of the bottom, and what we did was partial fractions to break it up, right? So we figured out that, here, this is what I want to show you. If you have some rational function p of x over q of x, and it factors into linear factors, ax plus b, right? That's what we mean by linear factors. Then it's possible to write a, what's the word? It is possible to write a partial fraction decomposition. There we go. Okay, and then the partial fraction decomposition. Holy crap, that is like really hard to say for some reason. The partial fraction decomposition is some number over each of those linear terms added together. Okay. So like I showed you how to do that. We did an example for it. It was like a lot of work. We like went through, we did it, blah, 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 blah. Okay, so we're going to continue today with more complicated examples. Or different types. Different partial fraction decompositions. Okay. So let me give you an example of one. Okay, one second. Like my thing is like stuck. Why is this like not going? I don't know. Okay, there we go. Okay, wait, I need Wolfram to multiply something for me. 1 second. Okay, so there we go. So let's say that you have x minus 2 over 2x minus 1 squared times x minus 1. Okay, so if you like multiply out the bottom, what you get is 4x cubed minus 8x squared plus 5x minus 1. Okay. So you look at this and you're like, okay, cool. If I needed to integrate this, maybe I could use U substitution, but there's sort of a problem with what's going on here. So if you look at your bottom, it does factor into linear factors. But no one said anything about one of those linear factors being raised to a power, right? Like, we have 2x minus 1 squared. Like, we have two different ones. So now you start wondering, like, well, what's going to happen? Because you would think that this would split up into something like a1 2x minus 1 plus a2 over x minus 1. But if you were to try that, this actually doesn't end up working. Okay? And it doesn't end up working because of the power. So these are called repeated linear factors. So whenever you have something of the form a1x plus b1 to some power n, that has a special name. It is a repeated linear factor. And what you need is you get a different term in the partial fraction decomposition for each of your powers. So let me explain what I mean by this. So like, let's say that you have 1 over 3x minus 5 to the third. 3x minus 5 to the third is a linear factor, yes? Okay, but what you're going to end up getting is, in your partial fraction decomposition, is an a1 over 3x minus 5 plus an a2 over 3x minus 5 squared plus an a3 3x minus 5 cubed. So that's what I mean by you need a term in the partial fraction decomposition for every single power of your repeated linear fraction factor. Holy crap, that sounded really long, so I'm going to type it. You need a separate term for each power of the repeated linear factor. So if you have a repeated linear factor to the third power, you're going to need something over that factor plus something over that factor squared plus something over that factor to the third. Right? So does that make sense? If you had like a fifth power, you'd have to have 5 different terms in your partial fraction decomposition. So let me just give you a moment to write that down. So for the one that we're doing, you would need an a1 over 2x minus 1 plus an a2 over x plus 1, but you're also gonna need like an a3 over 2x minus 1 squared, right? Because you have the square. So let's do an example of those. Crap, things are everywhere. Ugh, my pants are uncomfortable. Okay, so let's do this partial fraction decomposition. Okay, so I'm gonna have my x minus 2 over 2x minus 1 squared, x minus 1 equals a1 over 2x minus 1 plus a2 over 2x minus 1 squared plus a3 over x minus 1. Okay, so what am I going to do? I'm going to multiply by the denominator on both sides like last time. So I'll multiply by 2x minus 1 squared over x minus 1. 2x minus 1 squared over x minus 1. Okay, obviously on the left, those cancel. That's not very hard. So on the left, I'll get x minus 2. Now on the right, I'm going to get a1 times the terms that are not 2x minus 1. So I'm going to get 2x minus 1 times x minus 1 plus a2 x minus 1 plus a3 2x minus 1 quantity squared. Okay, so we're gonna do what we did last time. So on the left-hand side, you can think of this as 0 x squared plus 1x minus 2. Okay, right, so remember what I did is I multiplied everything out and I collected all the different terms. Okay, so like this 2x minus 1 times x minus 1, that's going to be 2x squared, and then you're going to get minus 2x minus x, so minus 3x plus 1. This is just x minus 1. This one is going to be 4x squared minus 4x plus 1. Did I multiply out that third one right? The 2x minus 1 squared. I feel like I did it wrong. It's like so hard. No, wait. See if anyone has anything to say about me doing that wrong. I feel like 2x minus 1 quantities. It looks right? Okay, we'll go with it. Okay, so now we start gathering terms. So let's gather all of the x squared terms. So if I have a 2x squared here, I'm going to have a 2a1, and then I'm going to have a plus 4a3 quantity x squared. And then plus, now I'm going to do the x terms. I'm going to get minus 3a1 plus a2 minus 4a3. And then plus, okay, constant terms are going to be a1 minus a2 plus a3. Okay, so this is just like what we did last time, right? There's just more terms. Okay, so now we set up our system of equations. So we're going to get 2a1 plus 4a3 equals 0. We're also going to get minus 3a1 plus a2 minus 4a3. I forgot to write the x for the second group of constants. Oh, thank you. Boom. That's a good catch. I missed the x there. Actually, what we're going to do is we're going to make that more beautiful. Let's move everything to the side to give me space to put my x. Oh my god, look at this. Isn't that so cool how I can just like move it over and then I'm like, X. Like, that's actually pretty amazing. I feel bad for you if you copied me blindly and then like, you know, you're going to have to erase it. You and your IRL real paper. So anyways, back to setting the constants. So you get negative 3a1 plus a2 minus 4a3 is going to be equal to 1. And then you're also going to get a1 minus a2 plus a3 equals minus 2. Okay, now this first one here, this one works out really nicely for us. Because it allows you to get rid of one of the variables, right? So should we get rid of a3? Let's get rid of a3. So if you solve for a3, you're going to get 4a3 equals minus 2a1, which means a3 equals minus 2/4, which is minus half a1. Okay, so now we can simplify these things. So you're going to get minus 3a1 plus a2 minus 4 times minus 1/2 a1 equals 1. So these two minuses are going to cancel. 4 divided by 2 is 2, so you're going to get plus 2. Minus 3a1 plus 2a1 is going to be minus a1. So minus a1 plus a2 equals 1. Okay, same thing for the one on the right. a1 minus a2 plus your a3 is minus 1/2 a1. That's equal to negative 2. a1 minus 1/2 a1 is 1/2 a1 minus a2 equals minus 2. Woo! Goddamn. Jesus. Sweet baby Jesus. Okay. I'm going to pause because I think people might be writing. Okay, so let's just solve for a2. a2 equals a1 plus 1. So we'll put those two equations together and we get 1/2 a1 minus a1 plus 1 equals negative 2. 1/2 a1 minus a1 is minus 1/2 a1. Distribute the minus, you get negative 1 on this side. If you add 1 on that side, you get equals negative 1. The minuses will cancel. We'll multiply by negative 2. So you get a1 equals negative 1 times negative 2 is positive 2. Oh my god, that's like victory. Holy shit. We got a number. Yes! Woo! Okay, so now you can plug that in somewhere. Let's plug that a1 equals 2 into here. And then you get a2 equals 2 plus 1. a2 equals 3. Pat yourself on the back. You got a new number. Okay, so if a2 equals 3 and a1 equals 2, oh, you can actually plug that into here. So 2a1 plus 4a3 equals 0. So what is a1 equal to? a1 is equal to 2, so you get 2 times 2, which is 4, plus 4a3 equals 0, which means 4a3 equals negative 4, which means a3 equals negative 1. Yes. Now I'm just going to leave that there for a moment. Hopefully the arrows sort of help you figure out like the flow of thinking. I'm going to pause and just let you look at it. Yeah, actually that probably would have been easier, yes. I just didn't notice it for some reason. Yeah, no, I completely agree. I just like that was like the first one my eye rested on because like I just looked at it and I was like, okay, this one would work. But yeah, you're totally right. It would have been just easier to plug that into there because it would have been like, oh yeah, what's negative 1/2 times 2? Yeah, negative 1. Boom. That actually is a really good point, right? So I totally get like maybe that's somewhere in my mind I remembered that because like you're right, like if you did make a mistake, like it's sort of interesting the way this works because if you make one mistake somewhere, everything after that is wrong, right? And it's like so hard sometimes to fix your work when you do this. So, but yeah, I mean anything technically will work. I do think it is good advice to plug it into the original though. Okay, so what does this give us? Well, it tells us now that x minus 2 over 2x minus 1 quantity squared times x minus 1 is equal to a1, which is 2 over 2x minus 1, plus a2, which is 3, and that's going to be over 2x minus 1 quantity squared, plus a3, which is negative 1, which is going to be over x minus 1. Okay, awesome. Now, why do we give a shit about this? Well, because I want to find the antiderivative of this thing, which means I can just find the antiderivatives of those things. And some of these are easy to do. So like for instance, this one right here would be 2 natural log of 2x minus 1. This one will be minus natural log of x minus 1. Don't forget your plus c. Let's do this one off on the side. I have an integral. Let's take 3 out. You're going to get 1 over 2x minus 1 quantity squared. I would set my u equal to 2x minus 1. Then what's your du going to be equal to? 2 dx, right? Okay, I only have a dx, so I'm going to get du over 2 equals dx. So I'm going to rewrite this as 3 integral u to the negative 2 du over 2. So I'll get 3 halves. Now what's the antiderivative of u to the negative 2? It's going to be u to the negative 3 divided by negative 3, right? Those 3's are going to cancel right there. So what that is going to give me is 1 over 2. My u is 2x minus 1, and it's going to be raised to the 3rd power. Boom. Yes. I forgot that minus. That was good. That was a good catch. there's your antiderivative in all of its glory. Boom! It worked. Holy crap. Okay. Okay, so I'm not really anal about that, but what does the graph of natural logarithm look like? Where does it hit the x-axis? Cool. So it looks like this, right? So what do you know about the domain of natural logarithm? What is it? Not 1 to infinity. 0 to infinity, right? The domain is all positive numbers. So technically you should be putting absolute value symbols whenever it's possible that something could be negative. So for instance, is it possible for 2x minus 1 to be negative? So you should have the natural log of the absolute value of 2x minus 1. But what about x squared plus 1? Is it ever possible for that to be negative? So you would just write. But then I don't really care about this. I presume that you... Does that sort of make sense? Like, that's just like... it makes no difference really in some sense. Like, you could just, like, if you want, just slap absolute values in there all the time. There's nothing wrong with that. For the most part. Because if they end up being positive, they're positive. But yeah, that should explain basically when you have to put them. Mm-hmm. Okay. Woo! Boom. Okay, so we talked about what to do if you got your linear factors. We talked about what to do if you have repeated linear factors. Oh, okay, this one's going to be fun. So let's look at this one. So let's say you're looking at 2x minus 3 over x cubed plus x. Okay, so if you factor out an x from the bottom, you get x squared plus 1. So what sort of factors do I have on the bottom? What sort of factor is the x term? Yeah, it's linear because it's 1 times x minus 0. But what about this one? Yeah, so what do we call it? We have a special name for this one. Yeah, so it's called an irreducible quadratic. An irreducible quadratic is a quadratic that you can't factor. Okay, that's different than, say, x squared minus 4. Can you factor x squared minus 4? Yes. So that is a reducible quadratic. Why? Well, because the damn thing can be factored into 2 linear terms. Does that sort of make sense? Like, there are reducible quadratics that you can break into linear factors, and then there are irreducible quadratics. Does anyone know what sort of roots do irreducible quadratics like this one have that make them unfactorable? No, this does not touch the x-axis. They only have imaginary roots, yes. You were very, very close there, though. There is a particular type that only touch the x-axis, yes, but this one in particular only has imaginary solutions. It never touches the x-axis. Okay, so you look at this and you're like, well, what the fuck am I supposed to do now? Like, I don't have linear terms. Like, what the hell? So this is the rule. Throw in the towel. I like Matthew's thinking. It's just like, do you know what? It's just not in the rule book. Like, I think, we get a mulligan on this one. Refresh the page. Maybe Infinity will give me a different problem. I know. Sometimes I feel that. That's a mood for sure. If you've got an irreducible quadratic, though, it's going to be of the form ax squared plus bx over c. So if this is irreducible, the term you get in your partial fraction decomposition is not just a on top here, but ax plus b. That's the term you get in your partial fraction decomposition. Yeah, it makes life really shitty. I think Sid agrees with me. You look at this and you're like, oh crap, fuck this. Now, this is gonna be better. Listen to this. What about if you have something like this? This is not just an irreducible quadratic. What do we have now? So this one, the 5x over x squared plus 1 cubed, this is not just an irreducible quadratic. What would you call this one? Yeah, it's a repeated irreducible quadratic. And guess what you're gonna get for this bad boy? Oh man, guess. You're gonna get a term for each one. You're gonna get an a1x plus b1 over x squared plus 1 plus an a2x plus b2 over x squared plus 1 squared plus a3x plus b3 over x squared plus 1 cubed. Doesn't it go all the way up to f? What do you mean by like all the way up to f? Oh, I mean, you use whatever the hell you want. Mathematicians usually like to use just a and b, and you. Okay, why is it nicer to use like a1 x1 plus b or a2 x2 plus b2 as opposed to like cx plus d? Like, why is my way better than like using a b c d e f? Yeah, you know how they relate to each other. And in fact, looking at this one, because it's a2, b2, you know that it's the square of your irreducible quadratic. Yeah, and if you just use the alphabet, you can just run out of letters. Like, maybe I make it so there's like 5 different terms. And soon you're like, well, what the hell am I supposed to do? I'm like on x, z plus y, you know? And then like, the next one, you're going to be like z... Or, sorry. You're gonna be like your x plus y and then plus, zx plus, and then you're like, uh-oh, what do you do? Like, go back to a? Start using Cyrillic methods. Yeah, it's really annoying when you use, what's it called? The regular alphabet or some other alphabet. So it's just easier to put like a index on them so that you know which one you're dealing with, because you'll never run out of numbers. You can run out of letters, but you'll never run out of numbers. Okay. So let's do this calculation. So we're like, okay, I've got 2x minus 3 over x times x squared plus 1, which is going to give me an a over x plus a1x plus b1 over x squared plus 1, and then plus a2x plus b2 over x squared plus 1 squared. Yeah, that looks good. Wait, I'm stupid. There's no square here. I don't know why I wrote this term. I'm just off today. My bad. I don't know what I was thinking. You only need those two, right? Because there's no square. Oh, I was thinking this because of my example, right? That I had made, right? Where it was squared. Okay, cool. So, I mean, what are we going to do? We're just going to multiply like we did previously. So we're going to multiply by x squared plus 1, x squared plus 1. Those cancel, giving me 2x minus 3. Okay, now we distribute. So you get a x squared plus 1. And then you get a1x plus b1 times x. This one's not that bad. Yeah, it's not that bad. Okay, so then we do the same shit as before. Okay, so you're going to get 0 x squared plus 2x minus 3. Right, I'm just writing that so you can see the coefficients, because we know that we're going to end up with x squared terms, right? So you might as well just identify the fact that that's 0 already. Okay, so now you go around. I've got my a x squared. Okay, and then you gotta find the. Oh, actually, wait. No. We should just distribute this x right here. So you're gonna get a1x squared plus b1x. Okay, because then you end up with a plus a1x squared. Now you look for the x terms, that's just b1. Now you look for the constants, that's going to be a, yeah, just a. Okay, I'm going to pause and let people look at this, because I just have a horrible feeling I might have made a mistake. And we'll find out momentarily if that's the case or not. So yeah, let's just highlight. I wish I had like a highlighter. Oh crap, I do have a highlighter. I was just like, I have a highlighter. So like, if you look at this term right here, that's ax squared, right? And if you look at this term right here, that's a1x squared. Okay, the highlighter's not really working for that one, but whatever. So you can factor out the x squared from both of them, so you get a plus a1. And then a similar thing for right here, that's your only x term, right? So it ends up right down there as b1x. And then you have a 1 right here. That's your only constant term, so that's why you get the a right there. So I just grouped everything in terms of whether it was a coefficient of x squared, a coefficient of x, or a constant. Yeah, I mean, my mind's sort of struggling too. I think I've just done this so much that I can sort of do it on autopilot. It doesn't like require conscious thought on my part anymore. Yeah, I know. You guys are all like, not cool, dude. Screw you. Not fair. Yeah, actually, I don't even have to think about this at this point. Like, it's almost like wiping my ass. Like, not to be mean. Do you know what I mean? But I'm just saying, like I've done this so many times. So, like, you too can be like that someday if you study a lot. Yeah. Luckily, the system of equations is pretty simple this time around. Like, it's not too stressful on the mind if you do it a lot. So we set up our equations and we're like a plus a1 because that comes from the x squared equals 0. Okay, then you set your coefficient from the constant, which is just b1. That's going to be equal to 2. That's pretty nice. I've got my b1 already. Sweet. And then your constant, which is a, that's equal to negative 3. Actually, that's pretty cool. Like it literally just solves for you. Okay, so we have our b1, we have our a. So now we can plug the fact that a equals negative 3 into here. So if a equals negative 3, you get negative 3 plus a1 equals 0, which means a1 equals 3. Yeah! So you look at this and now you're like, okay, cool. My 2x minus 3 equals x times x squared plus 1. And that's equal to my a, which is negative 3, and that's over x, plus a1, which is 3x, plus b1, which is 2, over x squared plus 1. Now, why did we care about this? Well, because we want to integrate. So there's my integration symbol. To integrate, we're going to get negative 3 natural log x, right? Because you can factor out the negative 3, and a height derivative of 1 over x is natural log x. Now for the next one, I would do u substitution. My u is going to be equal to x squared plus 1. My du is going to be equal to 2x. So crap. It's not going to work for this one. Because you have a 3x plus 2. So what was the method I used to solve that? That is true. But I think that's... Yes, you are correct. That is a good catch. So we can separate them. So let's separate those bad boys up here. Okay, so I'm going to get integral 3x over x squared plus 1 dx plus oh crap, it's under my thing. There we go. Better. 2 over x squared plus 1 dx. Oh, okay, yeah. So we can actually do this now, right? So your u equals x squared plus 1. My du is going to be equal to 2x dx. I need that 3 there. So if we factor out the 3, we'll get 3 integral, and then so you're going to get 1/2 du there. And then you get 1 over u. Cool. Which will give us 3 natural log, well, 3/2 natural log x squared plus 1. Okay, so I did the one on the left. I'm gonna put a little line here. So you can see where the work for one thing. Because it makes sense, like, so I have my integral, I set my u, du equals 2x dx, which means that x dx is d over 2. I factor out the 3, which leaves me with the x dx. You get the du over 2. The 3 and the 2 give you the 3/2. Okay. Now we have to do the other one. I'm a goat. Oh my god, this one. Oh. What rule are we gonna use? We learned this a while ago. You're gonna use a trig inverse for this one. So if you factor out the 2, you'll get 2 antiderivative 1 over x squared plus 1. And if you go and you look, we saw that that was tan inverse. So this would be 2 tan inverse of x. Boom. So your final answer ends up being plus, it has a plus 2 tan inverse of x right here. And that is your antiderivative. Damn. Okay, that one at the end there was sort of exhausting. I think we're gonna end here. That just like, it's sort of funny because I was just saying like, oh, this is not that hard, I can just do it. And then now I did that one and I was like, wait, never mind, I'm pretty dead now. Sort of, yes, but tell me where. Oh, thank you. I thought you were gonna say like, you totally fucked up over here and it was all wrong, and I was just about to be like, no! I can live with that mistake. That's not that bad. Yes, the hole was fixed. It's there used to be the hole there, right?